Good morning, everyone. Welcome to this month's COFFIES Seminar. This will be our last seminar of 2025, and today I'm happy to introduce our speaker today, Andrés Muñoz-Jaramillo. I'm sorry if I pronounce it correct or not. So Andres is originally from Colombia, where he did his undergrad in physics and electric engineering. He came to Montana State University for his PhD, which he finished in 2010. His focus was solar dynamo simulations. After his PhD, he did a postdoc at the Harvard Smithsonian CFA and a Jack Eddy Fellowship also there. Then he became a researcher for Georgia State University in 2013. His focus during his postdoc and GSU years was historical data restoration, including foci, sunspot areas, and magnetograms, all focused towards the understanding long-term solar variability. Since 2017, he joined SWORI, and his focus has been on different applications of artificial intelligence. This includes space weather forecast, instrument calibration, pattern finding and pattern classification, integration of physics with AI models, and more recently, training and using foundation models. So today we will hear one of such AI application that is his recent project about an AI-powered surface flux transport model to measure high-resolution velocity fields and forecast magnetic flux emergence. Let's welcome Andres again, and Andres, you have the Zoom now.
Thank you. Okay, I'm going to share my screen. Do you see my presentation?
Yes.
Okay. This is work that I have not done on my own. This is work that we did as part of this year's Helio Lab. And it involves also some of the people that are present here in the seminar. So if you have any questions, you can also ask them. I think this is, artificial intelligence is one of the things that I find fascinating, and I am absolutely in love with. And what I'm going to talk to you about is what I would say perhaps is one of the most interesting concepts around it. And so there is a lot of potential here for building projects that are similar and will cater to the specific physics that you may be interested in. So I'm happy to chat about these kinds of things too, if you're interested. Okay, so as I mentioned, I didn't do this on my own. We did this together as part of the Helio Lab in this summer. It was, as if you are not familiar with Helio Lab or a Frontier Development Laboratory, it's an 8-week accelerated program. And we get together for 8 weeks and tackle a particular challenge. The researchers were Plinio Guzman, Nina Bonaventura, Nishu Karma, and Catherine Keegan. And on the faculty side, we had Spiros, Shay, and me. And then Vibhuti was absolutely instrumental. What you're going to see here is almost completely built on top of the aftermaps that Lisa Upton and Vibhuti produce. And so, but Vibhuti went beyond that. He made simulations so that we could compare perfectly what we were doing with aft under very control conditions, etc., etc. So, I just wanted to acknowledge that. So, as always, I always start with my conclusions. So, my take-home message. The first thing is what I just said at the beginning. From a scientific point of view, one of the most interesting and powerful aspects of AI is how it learns. And as we master these frameworks, it opens very interesting possibilities as scientists. So, and this happens by integrating the physics in the design of your architecture. So if you put physics models within an AI model to create hybrids, but you put it all within the learning framework that was traditionally used for conventional architectures, you can create these very compelling applications. And I think the idea is to think about the AI outside of the standard architecture, the neural network, for example. We implemented a surface flux transport code in PyTorch, so that we could combine it with AI modules that will facilitate some of the elements that are the basic ingredients of the surface flux transport. So that is basically where I feel like there is a huge potential. Typically we will treat the AI model as a black box, and then we will try to open it up. Now, I think as we become more sophisticated, what we can do is we can design our model so that the physics are directly extractable from within this model. And our results are very promising. And in particular, we're focusing on making these estimations of flows at the surface, small-scale flows, like an AI measurement of small-scale flows, and flux emergence. And this is pretty exciting because, at this point, the evolution of the active region seems to be possible. And then potentially, as we push things in time and with better in other forms of data, we could start talking about short-term active region forecast. But I will tell you a little bit about the issues that we're facing and the work that we're aiming to do next. So let me start with, the way AI learns and why is it so interesting from a physics standpoint. So, AI is something that has many definitions, and it's not formally, there is not like a formal definition of what AI is. So I will start with the working definition because I quite like it actually. So, AI, from my point of view and the point of view of the people that do AI here at Southwest, it's a set of trainable mathematical tools that help scientists achieve human or superhuman performance on a wide variety of tasks or satisfy a special need. And as scientists, we are particularly interested in those that will enable us to make new discoveries, derive new insights, draw conclusions, find trends, or make current workflows cheaper and faster. Okay, what I'm talking about is specifically focused on AI as a mathematical tool to derive new insights. So when we think about AI, to me, the transformative perspective of what AI is a mathematical tool that enables approximation. And this can be a function, it could be a distribution, it could be an operator. As long as we have data that underpins the function, the statistical distribution of the mathematical operator that we want to learn, it is possible to approximate it. Depending on the quality of our data and observations, our training data, we can get closer or farther from that approximation. But thinking about something that can approximate a mathematical construct is a very powerful way of thinking about AI. So the way this works is by establishing a connection between an input and an output through a differentiable model. So you have to have a set of differentiable mathematical operations that transform your input and project it eventually into the space of your output. Okay? It's very important that this model is differentiable. That's one of the things that is critical. And the second one is that you have to have a quantitative criteria that you can use to quantify how good this approximation is. Okay? Now, this also has to be differentiable. So once you have a differentiable model that maps input into output, and you have a mathematical function that defines success, you can gradually modify the learnable components of your differentiable model to enable that transformation that you're wanting to accomplish. And, if you note, I have not really said that this should be a neural network. It can be absolutely any mathematical operation. Like, in the last year, I have backpropagated and used like coordinate transformations, backpropagated through coordinate transformations. And in this particular case, we're going to be backpropagating through a numerical integration. So this is possible if that transformation can be expressed as a nested set of functions, where you have, a function that is like made of a learnable component, learnable weights, that is multiplying a function that is made of learnable weights that are multiplying a function that is made of learnable weights that is multiplying on your input. So in a programming language, this is basically multiple lines of operations of variables that use each other. But once you have something like this, then you can calculate derivatives of your optimization against any of your learnable parameters, regardless of whether this is linear or nonlinear, or etc., so that you can optimize these learnable parameters to achieve what you want to accomplish. And when you calculate derivatives with respect to your input parameters, you define a solution space that you can optimize through. And typically what we do is we do stochastic gradient descent in this like multi-dimensional space. And this space have a huge amount of dimensions. They can have a billion dimensions when you have a billion free parameters. Now, I conceptually find very useful to think about an AI model as not just a box that is green, but as something that is made up of an encoder that is a set of mathematical operations that project your input into a latent space. So this is like an intermediate transformation of your input, and a projection head that is a set of mathematical operations that project your latent space into the space of your output or your ground truth. Okay? This is very powerful because, as you can see, this is like, this kind of like makes it more actionable. Your ability to interact with AI becomes more effective when you think about AI in something that is made of components. Now, these latent spaces are fascinating because you can actually influence the nature of your latent space. So you can do an intermediate, like a partial projection into a space where distance is similarity, for example. Or you can, make a projection into a space where different metrics have different meanings. Or you could project into a latent space that is physical. It is possible that the physics that you're interested in are not directly extractable from your output data. So let's say, for example, you're talking about densities in the corona, but ultraviolet photons are not densities. So if you have a way in which you can project a latent space that is of your interest, which is densities and temperatures, into an ultraviolet image, and that projection is differentiable, that can be part of your AI model. So you can have a latent physical space, as I said. You could have physical space transformations. For example, one of the things that I was telling you, you have data that is in plane of the sky, and your encoding includes a projection, a coordinate transformation into a latitude-longitude grid. Or you could work on a latitude-longitude grid and then do a projection into plane of the sky, so that you can compare with your ground truth, which are images taken by SDO. You can also have the ability to influence and prioritize different physical aspects of your learning. So you can calculate errors directly on your output data that evidence problems with the physics of your system. But actually, even though I don't have a connection here, you could calculate errors on your latent space so that your latent space is physical. So if your latent space is magnetic fields, you can calculate an error that is divergence. And if your system is not divergence free, it will introduce an incentive so that you can harness your learnable components to ensure that your latent space is what you want it to be. Now, there is something really cool about these approaches, which is that, within your AI model, you already have something that is directly ready for physical interpretation. These tend to be significantly smaller and cheaper to train than general purpose counterparts. So if you think about the state of the art when it comes to abstraction right now, which is the transformer that has millions, potentially billions of free parameters, you can accomplish competitive performance when you use physics and tens of thousands of parameters. So you can be orders of magnitude smaller and nimbler than the most powerful architectures that we're using if you combine your physics into your model. And the idea of approximation to reality is something that we live in. And the whole mathematical underpinning of artificial intelligence is built on the demonstration that approximation is feasible. So, there is always, it's proven that you can approximate these kinds of things. So you have to be disciplined and careful, etc., etc. There are pitfalls, but you have this power. So, the idea is then that if we think about AI models as hybrids that can be anything and have any mathematical operation, you can do optimizations as part of the optimization. You can do numerical integrations of both differential equations and integral equations. You can do anything you want, coordinate transformations that are just trigonometry, anything, anything that is differentiable, you can put in. So the goals of this project were the following. Was first, to deliver high-resolution forecasts of active region emergence with uncertainty quantification, to synthesize knowledge using AI, but put it in the context of physical quantities, in particular flux and flows, to integrate all the data that we have available in the form of Solar Dynamics Observatory to enable this, to enhance and elevate surface flux transport, and ultimately then to use this to make a meaningful statement about small-scale flows, flux emergence, and how they are connected. Our inspiration is a climate forecasting code that I discovered earlier this year called CLIM ODE, where you have a sequence of measurements of geophysical quantities. Based on this, you pass this through, you have a guess of what the velocity is that will transform these quantities. Then you integrate them in time in a transport code, classical, fluid dynamics on the atmosphere. You combine this with a differentiable model that turns your quantities into measurable forms of emission, radiation on the surface of the Earth. And then you compare this against your future. And then you backpropagate through this to get our forecasts of things like, humidity and pressure and temperature and things like this. And what I found fascinating is that this model was competitive with the biggest model that we currently have for climate forecasting, which has billions of parameters and is like a huge visual transformer. So here is again the little schematic that I show you, conceptual schematic that I show you, where you can put your physics. In the climate forecast, you will have as your input space velocities and the derivatives of those velocities in time. Then you will encode them into derivatives of the velocity. Then your projection head is the Navier-Stokes integration that will tell you what the velocity and the quantity that you're interested in is at the next step. And so in the same way, what I'm going to show you right now, we built a model that takes as an input AFT maps, active flux transport model maps, from the one produced by Lisa and Vibhuti. And it has an encoder that takes a sequence of maps and makes a guess on what the velocities on the surface of the sun are. And where are we going to have flux emergence? And then our projection is a differentiable integration of the surface flux transport model that produces a prediction of what the surface of the sun looks like and the magnetic field at the surface of the sun looks like, in which we imprint what we guess was going to be flux emergence, and then we calculate our loss and backpropagate. Our losses is the mean square error. So this is the basic loss that we typically start with in AI. And in the context of the physics of surface magnetism, is kind of like focus on ensuring flux, unsigned flux conservation. And we have a likelihood loss that we use to make uncertainty estimation. So I'm going to now take you through the implementation of the surface flux transport and the logic of where we fit in the current state of the art. So as I said, the data that we're using are the maps from the advective flux transport code, okay? So AFT maps have the surface of the sun in latitude and longitude, okay? And there is a part of the surface of the sun that is visible and a part of the sun that is invisible. So it's in the far side, and we don't have direct measurements on that. So for the part that is visible, AFT maps use the part that is visible from observations. So the observations get directly imprinted on the map. And for the rest that is not visible, it gets advected through the AFT model. So as time passes, everything that is invisible evolves like realistically, given a prescribed set of flows. And then when the part of the sun becomes visible again, then that gets overwritten by the visible side. Okay. So it combined the simulation of the surface flux transport with observations. The non-visible surface is evolved by AFT, and the visible surface is blended into the simulated map. It overrides the simulated map. Now, a surface flux transport, just like a quick introduction to surface flux transport, is an integration of the induction equation. So the induction equation tells us that the derivative of the magnetic field at the surface, like the derivative of the magnetic field in the sun period, is governed by a process of diffusion, so the diffusion of the magnetic field itself, and advection, so the interaction of the magnetic field with plasma flows. Okay? These velocities and the magnetic field are vectors, three-dimensional, and they depend on space and time, so they change in space and time. Okay? Now, to do flux transport, we do some manipulations to this equation. The first one is we limit ourselves to the surface of the sun, the photosphere, okay? And we approximate the magnetic field of the sun as a radial at the surface. That means that now it becomes the derivative of the magnetic field, the radial magnetic field at the surface, as governed by a diffusive and advective transport, okay? So these are the same terms, but now the only you have velocities at the surface, latitude and longitude, velocities in latitude and longitude, two-dimensional velocity vector, and you have a scalar that is covering the surface, the radius of the radial magnetic field. Now, because we're only simulating the surface, we add a term that is called the flux emergence term, that basically accounts for the fact that a lot of the flux that we see at the surface comes from underneath, from the interior of the sun. And so in a traditional surface flux transport model, this is prescribed. There is a term that adds gradually, the change of the surface magnetic field, the radial surface magnetic field, is governed by a process of addition of flux that comes from the interior. Now, then this gets integrated numerically, which here, I am approximating in the simplest possible form to say that the future in a surface flux transport model is dictated by your present plus a process of diffusion, advection, and flux emergence. Okay? Now, when we use surface flux transport operationally, like aft and adapt, we made this following modifications to the surface flux transport. The first one is that we remove the explicit term of flux emergence. The second one, as I mentioned before, we divide the computational domain into two different spaces. You have the non-visible computational domain, in which the evolution is governed completely by transport. And we have the visible part of the computational domain, in which the evolution is driven by observations. So where we see, we use the observations. Where we don't see, we transport. Okay? Now, operational surface flux transport then prescribes flows and imposes the observations as a form of emergence, and then focuses on long-term forecast, making sure that we have a complete picture of the surface of the sun at all times. Arcade, which is our project, infers flows and flux emergence and focuses on short-term forecasts. So it's kind of like, whereas something like aft is now working on timescales of solar rotations, Arcade is working in timescales of hours. So we use an existing framework for integrating ordinary differential equations called torch-diff-ec. This is in PyTorch. We work with latitude-longitude coordinates like aft. Our numerical integration in time is a Runge-Kutta scheme of 8th order, and that is implemented directly in torch-diff-ec. And the cool thing about torch-diff-ec is that it enables backpropagation. So you can backpropagate when you're training your AI model through the numerical integration in time. We do the partial derivatives in space. We work with a center 8th order stencil that we implement as a convolutional layer. So, taking a derivative on a gridded data in a uniform grid, you can think about it as a convolution. So you take several points and you take differences between the, forward and backwards and the center, etc., etc. So we implement this as a convolutional layer. We specify the weights of the stencil. This is not learnable, but it could be made. Or we could use different stencils if we want, but we have used center, and then we convolve with the data to take the derivatives. And we use periodic boundary conditions in longitude and zero boundary conditions in latitude. And we use a uniform grid. So our grid is uniform in latitude and longitude. So the first thing that we did was compare with aft. So Vibhuti made a bunch of different simulations of the evolution of the magnetic field only given transport without imposing the observations on the visible side. And so we took those as inputs to our, PyTorch surface flux transport implementation, and then we evolve this in time and compare against it. And so what you're looking at here is the evolution of the magnetic field 24 hours after the input. And here in our scale, we're using the HMI scale, where the magnetic field is positive if it is green and blue, so it's pointing towards you. and negative if it is red and orange, so it's pointing into the screen. So this is the latitude longitude grid, and here is the scale. So what you're seeing here is kind of like clamped around 500 Gauss. The difference that you see here is using a different color scale that is now positive and negative, but you can see that, you know, we're talking about errors of the order of 4 Gauss compared with aft. And here is an evolution of the error, of the distribution of error across the entire computational domain as a function of time for the 24 hours of evolution. And we did this for different times as well. So you can see, you know, that in general, the median error is about is a fraction of a percent, with, you know, extremes that are like around 1 to 2%. And then after the more structured part of the magnetic field diffuses, then the agreement between aft and our implementation increases. But, you know, we're talking about errors of about 1% compared to aft. So the last thing is to show you some of the results, you know, and the idea that these hybrid models shows great promise in inferring surface flows and identifying flux emergence. But of course, you know, it's not all perfect yet. So I will tell you also about some of the issues that we're facing and you know, the things that we have planning moving forward. The first thing that I also want to start with is a complete description of the model now that you understand conceptually what all the different pieces are. But there is one additional component of uncertainty quantification that we add here that I wanted to explain so that you have like the complete picture. So as I told you, AI learning frameworks and AI itself can approximate mathematical functions, operators, or distributions. So uncertainty quantification here is a way that we have of approximating the distribution of possible values for a given pixel within our computational domain or grid point. Okay. The idea is that when you have an AI model, you are optimizing a solution space made out of your weights, the training component of your AI model, okay? And that optimization is done through these learning frameworks as a gradient descent, a stochastic gradient descent. So we take some of the training data, we calculate and backpropagate gradients, and we take a step in the solution space. And then we take another subset of your training data, you calculate your gradients, and take another step guided by those. So there is a lot of randomness to this process because you don't show all the data. So your solution space, the one that you're traveling through, changes with every batch of images that you're backpropagating through your model. But that is actually, people have found that to be actually an advantage in making sure that your model is more generally applicable and is not hyper-fitting when you try to do it with all the data at the same time. But then the reality is that you have a solution space that you're trying to find and traverse through and find an optimum. But this optimum has a shallowness or a depth that changes depending on your data that you're training with and the model that you're using to train. So even though if you find an optimum, there is not a guarantee that the vicinity of that optimum is not also a good enough solution given your training data, given your model, given your... So uncertainty quantification in these kinds of models, a big part of it is trying to get a sense of the neighborhood of your optimum in the solution space. And the way we are doing it right now is from the perspective that there is a distribution of possible solutions living around that optimum. And we use a AI model to approximate that distribution. So whenever we make a deterministic forecast, we make first a deterministic forecast. We say this is what our magnetic field is going to be 6 hours into the future, right? And then we pass this through an AI module that is learnable, that based on, for every pixel in a grid point in our domain, makes a guess of what the mean is of that prediction, given the training data that we're using, etc., and what the standard deviation is for that particular pixel, given the input data, the model that we're training, etc. And then what we do is we add this as a residual to our deterministic forecast, and we use that to define a Gaussian. And then we take the standard deviation. So the mean of our Gaussian is going to be our deterministic forecast plus the residual that this uncertainty quantification module is producing, and the standard deviation that it is producing. And so now, then you can introduce another component to the loss, to the optimization function, which is log likelihood. A log likelihood. Basically, what we're trying to maximize is the likelihood, given a standard deviation and a mean for every pixel, that as we train our model and we're sampling all these possibilities, that this is well captured, or as best captured as possible, by this Gaussian. And so that is the last part, the last component of this model that you will see. So the arcane model, which is 20,000 parameters, 20,000 free parameters, which, to give you to put this in perspective, the foundation model that we released recently has 366 million parameters. So as far as model goes, it's pretty modest, actually. It's built on an architecture called a ResNet. So the ResNet is a convolutional neural network that is built inspired by the way our visual cortex works. And so it is an architecture, an AI architecture that is designed to leverage neighborhoods and the relationship between using the neighboring points as context to make a statement about the structures that you have in it. So this is a ResNet, and what makes a ResNet is that you have something called a skip connection. So you have convolutional layers that pass through your data and transform your data, but every so often you add back the input, and that now you modify with the next set of convolutional layers, and then you make a connection, and then you modify with another set of convolutional layers until you get your stack. Okay. So in the results that you were going to see, we're using 24 hours of aft maps, 6 hours at a 6-hour cadence. Okay. We put this through a ResNet, okay, that takes as an input 4 maps, and then as an output it produces three scalars. 2 of them are my velocity in latitude and longitude, and the third one is a guess of where flux is going to emerge on the surface of the sun, given these 24 hours of observations. Okay. Now, once we have that, we take the last one of these, which is our input, and we take our flows and we integrate in time, 6 hours into the future, using pure flux transport. Okay, the one that we implemented in TorchDiff FAQ. And the flows have 2 components. There is a small scale flow that is produced by the AI, and there is a meridional flow and a differential rotation that are part of the integration. So this is also like you have large scale flows, small scale flows, and both together are used to advance time in 6 hours into the future. Then we take the flux that was forecasted and we add it to that pure transport forecast. So we have a pure transport forecast, we add the flux emergence to it, and we produce our 6-hour deterministic forecast. And then this is passed through the uncertainty ResNet that produces the probabilistic forecast with the uncertainty estimation. So what you're looking at here is an aft map that we chose to display this. At this time, there is going to be a flux emergence happening in this region and this region. So this is an active region that is evolving, and this is an active region that is growing here. Okay? This is the target. This is what we want to get. And our input is before. So you can see if I switch, if you focus on these active regions, you know, and I go, this is the target, so this is the future, and this is the input, you will see that they're smaller. So they both have grown during this period of 6 hours. Okay? Now, when we pass this input into the AI, the AI produces a set of small scale flows for this map. Okay? In some sense, when we're training this model in the training loop, what we're asking the machine is, for this data, what is the best set of small scale flows that will produce a future like the one that we see here? Okay, this is of course on our test set, so this is data that the model never saw. But this is kind of like what we're trying to get here, is that the present is evolved into the future by surface flux transport, but not only by global flows, but also by small scale flows. So the idea here is that this combination of flux transport with AI can produce these kinds of maps. And this is what the model is saying where the flux is going to be. Okay, so you know, this is self-explanatory. So the model says, based on the input that you gave me, this is where I think the flux is going to be added. So part of the evolution is explained by these flows, but not all of it. The rest, the model says, is flux emergence. So now here is kind of like the same flux emergence, but now shown with a threshold mask, I think, in just to highlight where the model is saying the flux emergence is happening. And then this is the output after you apply transport and flux. And this is the target that we were trying to get out. So I'm going to switch again, the output and the target. And this is the error of the target minus the output. So if you here look at the scale, now this is saturated at 1000 Gauss. So it's from between minus 1000 Gauss and 1000 Gauss. And the error, it's in the order of 100 Gauss. Okay. And then here is where the uncertainty is. So this is again the errors of about between 0 and 80 Gauss. So that's kind of like the sigma of that Gaussian that we attach to every single one of these pixels goes between 0 and 80 Gauss, given, you know, our process of training. So to finalize, let me just go really quick with our outstanding issues and future work. So the first issue that we're still that we have not completely addressed is that our flux emergence term is not pure. Okay, so because our flux forecast is very close to the optimization function, the AI kind of cheats. So it puts some things that should be transport as flux emergence. And so you can see it clearly here when I highlight this in this mask. So remember, these are aft maps. Aft maps have observation on the visible part of the sun and pure flux transport on the not visible part of the sun. So if this was perfect flux emergence, there should be 0 here, because an aft map has no flux emergence on the dark side of the sun. Of course, there could be a loss, you know, there could be a loss of magnetic flux in aft that then the machine will approximate as a sink, a flux sink. But I think, in this moment, we feel that that is not completely the case. So it is possible that with aft maps, this signal will never completely disappear, but in this moment, it's stronger than it should. Of course, one thing that is encouraging is that the strongest signals for flux emergence definitely happen on the visible side, and they happen when the active regions are. But there is this kind of like clear signature that to me are very clear signatures of transport mimicked through emergence. So you have this east-west where you have this flux that emerges here and sinks. So you have a source and a sink here, and that basically is just shifting an element in one direction. The other issue that we're having is that the small-scale flows are absorbing a lot of the global flows. So differential rotation, even though it's an ingredient, or meridional flow, which are ingredients, global flows that drive flux transport on the sun, and they are learnable as part of our ODE, our integration. They start to get absorbed by the AI. So the AI model starts doing at the same time small scale and global. And the signal of the global starts to dominate the small scale. And we wanted them separated. But this is the other issue that we still have. And so in this moment, we are implementing scheduling. So we're kind of like designing training schedules in which different components are trained independently from each other. So we start with global flows and we learn those first. And then we fix them. And then we do the small scale flows. And so we basically capture as much of the variability as can be captured with global flows first, then freeze those, then as much of the variability as we can with flows, then freeze those, and then we capture the rest of the variability with flux emergence. So these are ongoing experiments, so I don't have results to show you yet, but that's kind of like what we're hoping to address some of these issues to increase the purity of the signals that we're getting. And the second one is stepping outside of the aft map. So, by design, and because it's perfectly fine for the main application of operational surface flux transport to have a resolution of 1K by 500. That's the resolution that we're working with. But it has always been our goal to eventually do flux transport at the as close to the resolution of HMI as possible, full resolution of the instrument. That's one thing. And second, right now our input is sequences of magnetic maps, because we're using as an input aft maps, and it's just magnetic information. But we believe that if we can take advantage of Doppler, for example, or ultraviolet, we could have a better chance of doing flux emergence, for example, better. And so, that's the other component of this, is that once everything is now well validated within the aft framework, we would like to now train surface flux transport directly on HMI data with inputs into the models that are AIA and Doppler. So that's basically all I wanted to share with you guys today. So again, my take-home message, and I think perhaps the most important point, again, I would like to, is that AI can be physical if we are clever in how we design our architectures, and we are intentional in when we design our architectures. So we have discussed, for example, helioseismic inversions where the model is learnable. You have an AI model that produces a model of the interior of the sun, and you need a differentiable model that simulates the propagation of sound through it, that you can compare against helioseismic spectra, and then you backpropagate into the AI model to produce inversions of flows and fields. Or as I show you, as you may have seen our work when we are doing intensity and absorption in the solar corona, that the AI model is learning our latent space, which is what we want, intensity and absorption, or density and temperature. But we have a radiative transfer module that transforms densities and temperatures into ultraviolet images so that we can compare against AIA and backpropagate into that AI model. But our latent space is what we want, the measurement. So, AI can become a vehicle for measurements, physical measurements, given the existence of differentiable physical models. So it's really cool. And I hope, this application that we show you with surface flux transport is one of those that, makes you as excited as we are, because now it becomes super interesting. And these ones, they don't have to be bazillion parameters. They're like easier to train. Anybody can do them as long as they know their physics and their math. You don't need like the entire, a million GPUs to do this, etc., etc. So it brings also AI by leveraging our physical understanding and our models. It brings AI into everybody's computer. So we implemented the surface flux transport in PyTorch. Basically, the necessity is that everything you need to implement in your learning framework. So if you're going to be using PyTorch to train your AI model, your physical model needs to be in PyTorch. If you're going to use JAX, then your physical model needs to be in JAX. But you need to implement absolutely everything in PyTorch. Nothing can be in NumPy, nothing can be in SciPy, everything has to be done in PyTorch. So that is, I think, the barrier to entry. But it is possible, and there is a lot of things out there that you can use, like we did for the integration, like torch diff ec. And so, we implemented that surface flux transport model in PyTorch so that we can integrate everything. And the hybrid shows great promise in inferring surface flows and in identifying regions of flux emergence. It's not perfect yet, but I think, it's really cool because it also fills a niche that in this moment is not addressed by any models, which is short-term forecast of active regions. So in this moment, we either take the active regions are given and evolve them, or make a general guess of what active regions are going to be, but now at a cycle timescale, and evolve them. This one allows you to do short-term forecasts, 6 hours, 12 hours, potentially, and that has interesting implications both for physical understanding and space weather forecasting. So that's it. Thank you so much for your attention.
Thank you, Andre. I'm looking in. There I see a hands raised. Nick.
No, sorry, I was trying to click the
Okay, I was just checking the chats. But there were questions there, but were already answered. So
Okay, yes, I have not been able to keep an eye on the chat, but if there is anything else, please, can you guys let me know?
Andre, I have a question. So you were talking about the flux emergence on the far side, and I'm wondering, is that because a flux cancellation that isn't fully resolved looks like a flux emergence of the opposite sign, or is there some sort of mismatch in coordinates or rotation rates that's
Yes.
making it look like that instead?
So our quote-unquote flux emergence term is also, it's actually can be also a sink, and there are some, so cancellation then could be simulated as a flux emergence. Like if I have a pattern, I can impose a pattern that cancels my flux, right? And so in this moment, the issue that I feel we have is that some of the processes of transport are being co-opted by the flux emergence term. So for example, imagine you have a patch here and you just move it. You can mimic this behavior by subtracting it from here. So it's kind of like a loss of flux. and adding it to the side of it. So it looks like a flux emergence term in the way we put it, but we physically know that at that, for example, at that latitude, then it should be just pure transport. So diffusion, cancellation, some of these things are being absorbed by what we call our flux emergence term, and that's what we are working towards addressing. Does that answer the question?
Yeah, I think so. If you looked at different time resolutions, instead of doing 6 hours, doing something else, and your flux emergence term changed in some systematic way, that might give you a clue for how that's working. Another
Yes.
question I had was, you mentioned sort of earlier on that you had a periodic boundary function in longitude. Does that make sense? Why would you?
Periodic boundary condition.
Yeah, why did you? Yeah, if I understood it right, does that mean your left and right edges of your synoptic maps have to match up even though they don't?
But our maps are not synoptic maps; they are aft maps, so they match because they are meant to be an instant in time.
Yeah, they match, except that you've got all the flux that came out on the far side that you're going to start assimilating as soon as the aft map rotates over the east limb.
Correct. But I think
So-
but this is like I mean, a periodic boundary condition is the correct physical boundary condition for the system. Now, when we do assimilation, that may violate that boundary condition just because, there may be things that are not visible, etc., etc. But that is like a limitation imposed by the fact that we don't see the full sun. If we had the full sun, that boundary condition will be fully fulfilled. Yes.
Yeah, I guess I'm just thinking of, at high latitudes, you're not rotating in 27 days, and your aft map is a 27-day or, whatever map.
No, the app map is a latitude longitude map for an instant in time. It's not a synoptic map. The aft map, that's what makes the operational surface flux transport. When the aft maps are produced every hour, and every hour you have the state of the sun on that hour, giving a combination of data assimilation and surface flux transport. The aft map of the next hour will have evolved because of flux transport by 1 hour, and the observations also have evolved by 1 hour. So aft maps are not synoptic maps in that they are meant to capture an instant in time. Aft maps are not built like synoptic maps where every longitude corresponds to a different time. In an aft map, every latitude corresponds to a latitude, and the time applies to the entire map. Does that make sense? And Lisa, please correct me if I am mischaracterizing.
Yeah, no, that's correct. We often call them synchronic maps because they represent a map of the entire sun at a single instant in time, as opposed to a synoptic map, which is built up over the period of a Carrington rotation. That's correct. I did have one question, follow-up question onto Todd's question, though, and this kind of goes into the concept of flux emergence. And it sounds like your flux emergence is capturing multiple processes, including active region decay. Does it actually capture active region decay? So if you have an isolated active region that is just slowly decaying, is it capturing that as well? And is that included in the flux emergence map, so to speak?
So that term that we're calling flux transport is catching everything that is not well described by a process of diffusion and a process of advection, right? And so flux cancellation that happens because of diffusion is captured by the integration of the flux transport component. But if cancellation is not described properly by any part of cancellation that is not described solely by diffusion will be captured in that kind of catch-up term.
Okay.
Yes. Yeah.
Thanks.
So where the surface flux transport model breaks, be that because we're not fitting the global flows properly, or because our flows are not producing the right behavior, then that term that we call flux emergence will try to pitch in, right? And that's what makes our flux transport term kind of like impure. So the hope is that the better we capture transport, the more our flux, quote unquote, flux emergence term will be flux emergence.
And so, and that's why you say, like, for instance, on the far side, it really is emergence, not just flux cancellation, that's causing the pattern that you see on the back.
No, in
Although
this moment,
it could be
no.
negative emergence, so that it would
Yes,
cause
exactly.
cancellation, but
Yes.
it's not just the collision of different opposite flux elements, for instance.
Yes, and I think that, so how well can our AI model capture the aft turbulent flow pattern based on 24 hours limits our ability to really get those flows well. And so when those part of those flows that we don't get that drive aft, then they will be then fixed, quote unquote, by the flux emergence term. Yeah. So that's kind of like the limitation when it happens in the way we frame this.
So would it be beneficial, for instance, for a future step to maybe also include the convective flow maps as well as part of the learning process?
It will be in that we will then be able to match aft better.
Okay.
But we see the aft as a stepping stone towards just using it purely on the
Observations.
visible part
Right.
for which we will not have those maps. So
Yeah.
that's, I guess, so I think the thinking is that once we are starting to trust better these small scale flows, we want to compare them with aft for validation, right? And
Yeah.
then, so instead of fitting them to aft, compare to aft, and if they kind of like agree to a certain extent, then when we apply to real observations, we can have more confidence on what we're getting from the real sun.
I will just add, I think it's a bit of a misnomer to call them small scale flows. I would actually call them large scale convective flows, because they're on the scales of supergranules or larger. They're not capturing the convection smaller than supergranules. So just a
Okay,
bit of a note there.
I will refer to them as convective flows.
Yeah, thanks.
Robert?
Okay.
So I don't quite understand. So there's a distinction between your axisymmetric flows, your convective flows, if we want to call them this. I prefer small scale, and your source term. And to me, from the equation you had, these look all non-unique. And so it's non-unique. Yeah, I can understand this, but how do you then intend to make them unique?
So what we were thinking about is prioritize, like giving. So in this moment, our next experiment, I don't know for a fact that it's going to work perfectly, but what we're doing is going to kind of like rank them and prioritize them. So we will first feed the global flows, right? Given these aft maps for the solar cycle 24 and 25. What is the best differential rotation that is axisymmetric and symmetric across the equator that will give us the best performing forecast 6 hours into the future or 18 hours into the future, and the meridional flow as well. So we start with the published profiles for differential rotation, meridional flow, and we modify them so that we fit the aft maps maps as best as possible. And then we freeze those. So the working assumption there is that once we have the best possible estimation of the global flows, anything else is a small scale flows or a convective flow. And so then we will now bring the small scale convective flows or convective flows online, that component, and then we train the model again. Now, any errors that the global flows, things that the global flows are not accounting for will be absorbed now by the small scale flows. And then we train this until there is like a saturation on this model, and then we bring the quote unquote the rest, the flux, what we call flux emergence, the rest online. Now, there will not be complete purity on that term, but the hope is that the signature especially for anything that has to do with active regions, flux emergence will be a very dominant signal in that rest, And so that's kind of like the hope. In this moment, the results that you saw, all the parameters were floating and they were all trained at the same time. And so it was easier for the model to say, you know what, I can make do with just this term, which is quote unquote flux emergence. So that was kind of like what we were going to do next, is making it harder for the model to do that by fixing the other parameters in like hierarchically.
And why do you want to make the distinction between the axisymmetric and non-axisymmetric flows? I mean, I can understand you want to break out the source term because that's physically different, but the flows.
So what I think is interesting here is that when you include in this model the small scale, the convective flows, well, in some sense, what you're asking is what flow components, which are non-axisymmetric, given these observations, gives me the best match of the future, right? So in some sense, what I'm hoping this answers is that given the framework of flux transport, surface flux transport, what is the nature of these flows? Like, for example, the flows that are happening around active regions. I think those to me are particularly interesting. Now, when we are having flux emergence, how do the flows, the idea here is that anything that we get out of this model always has beside it given surface flux transport. So it is like, in some sense, is how does given surface flux transport, how do flows evolve in the sun as time passes and as activity comes and goes, emerges and decays, etc., etc. So, and I'm particularly curious what happens when we go into a higher resolution. So now we are kind of like, if this all works with AFMAPs, we're entering a domain of measuring transport, like surface flux transport flows at 4K resolution, And so I'm very curious to see, what those flow measurements, it's like a flow measurement estimation. What do they look like? And what they are at very high resolutions that are beyond what we normally deal with when we're working for flux transport. And so I think in this moment, I cannot tell you what I'm expecting to see, but that is the motivation for
But I'm just wondering,
separating them.
I still don't quite see because you can separate them post facto. It's just the M is equal to 0 component.
Yeah.
You can always, yeah.
Yes.
Okay.
We also have a hand raised from Yiming Wang. Yiming, can you?
Yeah, can you hear me?
Yes.
Yes.
Yeah. My question was basically the same as Robert's about the small scale flows. Those flows are stochastic. In other words, I don't see how you can predict them. And they will, so on short terms, time scales of a day or a couple of days, they basically they're a random component. And so I'm not sure how your algorithm can take care of that.
So the fact that we're using as an input a sequence, so the small scale flow component of the model takes as an input a sequence. In this moment, the results that you saw was 24 hours every 6 hours. So flows that are not random at the scale of the input can be potentially learned. And so that is, I think, the other reason why we make them explicit, and separate them from large scale flows. Because the average flow, the differential rotation that is stable for several rotations,
Yeah.
right? Or
Yeah.
for those get captured and learned by one part of the model, and then those that are evolving at time scales matching those of the input to the model can be also estimated. Now, anything that is changing faster than 6 hours will be ignored by the model, and because the model will see it as noise. So that will always be part of the error of the residual. So the time scale governing the flows that we can capture is determined by the sequence and cadence, the length and cadence of the sequence that we use as input. And that is in this moment not something we have played around with. But yeah, that's the idea here, is that that enables this kind of like something that from the point of view of a year or 10 years, the solar cycle will basically be noise.
So if you ignore the small scale flows, basically, well, why do you want to go to higher spatial resolution?
Because this is a surface flux transport applied to short time scales. So the niche that we're aiming to fill here is something that is shorter than a rotation. Because for a rotation or longer, we already have aft and adapt and surface flux transport, the conventional one. What we want to do is focus on timescales that are shorter than that rotation.
Yes,
And
but
in those timescales, these are not longer irrelevant flows. They become dominant for the dynamics of the short timescale.
but the small scale flows is supergranular convection. That is much shorter. That's shorter than the 1 month time scale, and
Correct.
it's 1 or 2 day time scale.
Yes,
But
so we are
but
doing,
you
that's our timescale, that's the timescale that we're using in this model
yes,
for
but
learning.
the question was, I mean, how are you going to predict those flows? They're stochastic. They're I I don't see how you predict them.
So
I
I
don't
mean,
think
for
you
instance,
predict them. I think you just you're essentially doing what AF does and making a realization that is consistent with what they might be. They may not be precisely the exact flows that are on there, but they are evolving from what was on there before, and so they should be consistent with what has happened, but just time evolved.
but
yes,
those
Right.
short-term flows, the supergranular convection, for instance, they all affect the coronal hole boundaries, the locations of the boundaries. They affect them quite a lot. And I don't know how they would affect active region emergence, but they do have an important effect, and I think they're not predictable on time scales. 1 or 2 day timescales. But maybe
So
it's not
what do
important
you,
for ag-
but is there a time scale in which you will consider them predictable?
The supergranular convection, the typical time scale is the lifetime of a supergranular cell. And I'd say it's difficult to predict, exactly what's going to happen on that time scale, because it's basically random, the location of the cell and how it
Right, but
changes.
if you have a supergranular flow pattern, right?
Yeah,
And you can measure it right now.
yeah.
Let's imagine that we can, how much time does it pass until that itself is changed in
Well,
your
if you
recognition?
measure
It
it
depends on the
at,
scale that you're interested in.
if you measure that, you take a particular supergranular cell and then you measure the flow at one instant of time. I would think a day or two later, it's difficult to predict, what the flow pattern in that region is.
But 6 hours?
No, 1 day, let's say.
Yeah,
1 day later.
what I'm saying is that what we're doing is a 6 hours, right? 6 hours forecast. And so the kind of like the
So
working
you
assumption
say,
here, the
so you're
working
saying
assumption,
the flow exactly every 6 hours, and then you predict it 6 hours later. Is that what you're saying?
so what we do is we look at the last 24 hours. Based on that, we make a guess for what these flows,
It's
the convective flows are going to be in the next 6 hours.
it's basically just an extrapolation
Yeah.
of the evolution from the past 24 hours. So you've got a set
Exactly.
of convective
So
flows
we
that have
see
been
supergranular
evolving.
flows evolving during the last 24 hours, and based on that, we make a guess for just 6 hours, no more. That's what this model is aiming for. No 24 hours, no 3 days, not a rotation.
Oh,
No, it's kind of like
okay.
a short-term horizon that we're focusing on.
Okay.
Lisa, you also have a question?
Well, I was just going to add that we do have a version of AF that does go at the full HMI resolution, and we also have done shorter time step series, so we can do those as well. And I think the other thing I was going to note is that in terms of the convection, because of the data assimilation, the convective cells on the near side are actually representative of the convection on the sun as opposed to the convective simulation. So just like the magnetic field is updated with the observations therefore the flows, the convective flows are as well. So on the near
Okay.
side. So
Okay.
just
I think
a point to note.
no. Yes. I mean, certainly staying within the context of aft is very good for us because it helps us validate. So going to an aft of higher resolution before we do just pure observations is good because this is a new application.
We can do that.
Yeah.
Okay, we are over time. We are significantly over
Yes.
time. But thank you for everyone for the very detailed technical discussion. That's I think very helpful. And thank you all for staying until now. Okay, so I guess we will see everyone in 2026 seminars. We do have a poll of the 2026 seminar time because every year people's schedule change a little bit, which I sent in the chat. But all Coffees people should have already received that link. But if you have not, due to some glitch in the email list, whatever, email me for the want to meet link. We are closing the poll for time availability very soon. So we would like to choose a time that works best for everyone. Thank you all and see you in 2026. Thank you, Andres, again.
Thank you,
Bye.
Andres. Great talk.
Bye-bye.